Stephen Hawking is the world's most famous scientist. He's on a quest to answer the biggest question of all. How did everything in the universe come to exist?
If we find the answer to that, we would know the mind of God.
Hawking's goal is to discover a blueprint for the universe. But he's locked in a battle with a disease that has left him paralyzed. And it's advancing. Can he unlock the secret of creation before his time runs out? Stephen Hawking is one of the greatest thinkers of all time. He's on a quest to understand the moment of creation when the universe is born. 20 years ago, he writes a book on the subject that becomes an international bestseller. It promises that soon he will have a single theory so powerful it will explain all the mysteries in the cosmos. Why did the universe spring into life? And will it ever come to an end? A theory of everything.
We are getting close to answering the age-old questions. Why are we here? Where did we come from?
His determination to find answers has kept him alive far longer than any doctor predicted.
Stephen has got tremendous determination to solve the problems of the universe. And I think that's one of the key factors which has kept him going all these years.
But he lives his life on borrowed time.
The idea that my father had a very short lifespan was always present. I think it was there every single day.
Hawking will not rest until he unlocks the secret of how the universe came to be.
My goal is simple. It is a complete understanding of the universe, why it is as it is, and why it exists at all.
Born in 1942, Stephen Hawking has always been fascinated by the world around him. As a healthy child, he wonders what made the stars. By the time he's a teenager, he wants to find out where the entire universe came from. In the 1960s, scientists have yet to answer that question. Many believe our universe had no beginning. It is timeless and unchanging. But a new theory gains ground. Everything in our universe exploded from one tiny point, like a shower of fireworks. Scientists nickname it the Big Bang. But how can we suddenly go from nothing to everything in one moment of creation? Just 20 years old, Stephen Hawking's first mission is to find out. In 1962, he's just started his PhD at Cambridge University, where he's eager to prove himself. According to his old friend Kip Thorne,
Stephen was beginning to develop a reputation at that stage, but just barely beginning. It was not at all obvious at that point that he was going to come to tower over all the rest of us.
But it's around this time that Hawking notices he's becoming very clumsy. A visit to the hospital leads to a startling diagnosis. Doctors discover he has amyotrophic lateral sclerosis, or ALS. The disease wastes his muscles. Before long, he will be completely paralyzed. Within 2 years, he will be dead. Hawking is just 21. His dream of unraveling the mysteries of the universe crashes down around him.
I had just been diagnosed with ALS, and I didn't know if I would live long enough to finish my doctorate.
It's the darkest period of his life. According to his daughter, Lucy Hawking,
He became very depressed and very saddened. He was casting around at the time for a PhD topic, but he didn't really see any point in going on, so I think everything seemed very bleak and very hopeless to him.
But then Hawking meets Lucy's mother, and they fall in love, despite his death sentence.
Getting engaged and getting married to her was for him the turning point, that was the event for him that turned him around and gave him hope and made him decide that he was going to carry on.
Hawking sets out to discover the origin of the universe before his time runs out.
Does the universe, in fact, have a beginning or an end? And if so, what are they like?
Scientists remain skeptical that something can come from nothing, as the Big Bang predicts. Hawking wants to find out. His first break comes in 1965. He attends a lecture by a brilliant mathematician named Roger Penrose. Hawking hears something that grabs his interest.
Stephen was in the audience at the back of the room, and he was asking some very pertinent and difficult questions.
Penrose suggests something astonishing. There's a hole in space where huge objects disappear. If matter disappears into nothing, maybe it can also appear from nothing. This could be Hawking's first step towards proving the Big Bang. But how can there be a hole in space? The answer might lie with gravity. Einstein's general theory of relativity says gravity isn't just a force of attraction, it actually bends space. Oxford University physicist Pedro Ferreira studies gravity's impact on the universe.
Well, Einstein realized that gravity wasn't this force that acted between two bodies. It was something much more elegant and beautiful.
Einstein pictures space and time as a fabric. Planets and stars press on this fabric and create dips. In a stroke of genius, he realizes gravity is not a force, but the bends in this fabric. The dips pull objects towards them.
Let's imagine this rubber sheet is space. These glass balls that I'm holding in my hand are planets and stars. Now, if you place a planet or a star in the universe on space, it'll create a dip. And the bigger the object you place, the bigger the dip. Imagine that the Earth is this coin, and I just send it coasting round our sun. It'll settle nicely into an orbit. It's just following the deformed nature of the fabric of space. That's what gravity is, and that's what Einstein realized.
So what we experience as gravity is actually the curve of space-time around us.
The theory of relativity does force us to fundamentally change our ideas of space and time.
When that fabric gets stretched to breaking point, something dramatic happens. A hole in space opens up. A hole down which things can disappear. This chain of events starts when a star dies. It begins to collapse in on itself, getting smaller and denser. If a star 20 times the size of the sun dies, it has a drastic effect on the fabric of space-time.
If you imagine what this means in terms of the fabric of space-time, you're just pressing down on it incredibly hard. You're pressing so hard on it that at that point, it almost tears.
The depression is so deep that nothing can climb out, not even light. This is known as a black hole.
If this star is big enough, it'll collapse to a tiny, minute point, incredibly dense. And it'll create a dip in space. so deep that if an object tries to pass by, it'll be sucked in, it'll be sucked all the way down into that point. That's a black hole.
Roger Penrose discovers that at the center of a black hole is a point of pure gravity. It's called a singularity.
As you go into a black hole, you will encounter something which goes against the laws of physics as we previously understood it. Roughly speaking, you could say a singularity is where space and time come to an end.
A singularity is like a drain, a hole in space. Everything that falls down it disappears. Hawking wonders if the opposite could be true. According to the Big Bang Theory, all the universe suddenly sprang from a point of nothing. Could this hole be the key to explain how this happened? In a moment of genius, he sees the solution. It's elegantly simple.
I soon realized that if one reversed the direction of time in Penrose's theorem, the collapse became an expansion.
Instead of sucking everything in, a reverse black hole explodes out in a shower of space, matter, and time. Exactly as the Big Bang Theory predicts. Against a sea of skepticism, Hawking proves the universe suddenly appeared from nothing. It sprang from inside a singularity. The debate is over.
The universe must have had a beginning in time. This was finally proved by Penrose and myself, on the basis of Einstein's theory of relativity.
Hawking found the origin of time, but he hasn't found a way to stop it ticking. He's now 26 years old. His disease has advanced up the muscles in his legs. He can no longer walk. But his brain is alive with questions. Hawking now knows a moment of creation happened, but not what caused it to explode into being. This will prove his biggest challenge yet. Can he find the answer before his body collapses? Stephen Hawking has discovered where the universe began. A tiny hole in space, known as a singularity. This exploded in a Big Bang to create everything in the universe. But he doesn't understand what made it explode.
Why are we here? Where did we come from?
To find the origin of the universe, Hawking used Einstein's general theory of relativity. Relativity explains how gravity acts on large objects like stars and planets. But when the universe was born, it was smaller than an atom. So to understand how it grew, he needs the theory of the very small. Quantum mechanics. The trouble is atoms are unpredictable. They don't follow the ordered rules of gravity. The theories of general relativity and quantum mechanics are incompatible.
Unfortunately, these two theories are known to be inconsistent with each other. They cannot both be correct.
At NASA Goddard Space Flight Center, Kim Weaver is interested in the conflict between the theories.
In a way, this ball can be used to represent the tension, or the battle actually, that's going on between general relativity and quantum mechanics, quantum physics. The surface is smooth. It represents a large scale. General relativity, gravity, acts on a very large scale. And we can predict what's going to happen based on those equations. But if we zoom into the quantum world, things are very chaotic, and these larger scale laws don't apply.
We used to think that electrons orbited around the nucleus of an atom like planets around the sun. But scientists now know that electrons pop up and disappear at random. They can even be in more than one place at the same time. Normally, gravity appears to play no part in this chaotic world. But at the moment of the Big Bang, there was a huge amount of matter held together in a tiny space. So gravity must have had a role.
Bringing these two ideas of general relativity and quantum mechanics together into a unified whole is what Stephen Hawking set out to do.
He wants to combine the two theories into a theory of everything in order to find out what triggered the moment of creation.
If we find the answer to that, it would be the ultimate triumph of human reason.
The theory of everything is the holy grail of theoretical physics. It has challenged the greatest minds for centuries. No one has ever found it. In 1971, Hawking faces a giant hurdle in his quest. He's locked in a battle with a disease that is wasting the muscles in his body. It progresses to his hands, and he can no longer write.
And that was the big transition, not losing the ability to walk. Because for a physicist to do research, a key thing is to be able to write down equations and stare at them. He couldn't do that anymore.
He will have to do all of the calculations in his head. It's a huge challenge. But Hawking has lived longer than any doctor predicted. He's used to beating the odds. His quest for the theory of everything inspires him to keep fighting. Hawking knows the theories of gravity and quantum mechanics clash at the instant of the Big Bang. But he believes they also clash inside a black hole. This is where a huge amount of matter crushes to a tiny point. So he returns to black holes to investigate. If he can unite the two theories here, it could help him understand the Big Bang. Relativity says nothing can exist on the edge of a black hole. Everything is sucked in. But quantum mechanics states that space is never empty. It's full of tiny pairs of particles.
Space is essentially empty to us, and it is empty when we look at it. It appears to be empty. But at this very tiny level, it's not at all. In fact, it's filled with virtual particles coming into existence and annihilating each other all the time.
Energy waves in space create tiny particles. Every particle has an antiparticle. One has positive energy, and the other has negative energy. These pairs appear, but then collide and destroy each other.
Quantum mechanics was very well established, but no one knew how it played into the larger scale of the universe. And that's where Stephen took those two things and said, let me now play with this in my mind. How does this work? If I put a virtual pair next to a black hole, what happens?
To unlock the secrets of a black hole, Hawking must discover what happens to these particles. Now 28, his body is wasting away, but his mind doesn't let him down. He has a flash of inspiration. The answer lies with the fact that the particles are positive and negative.
And what Hawking realized, what's really fascinating about this, is when a pair of particles like this appears near the event horizon of a black hole, the one with negative energy falls into the black hole, and the one with positive energy escapes as radiation.
The negative particle is pulled into the black hole, but the positive particle has just enough energy to avoid getting sucked in. It's released as a particle of radiation. Hawking has proved black holes give off heat, and these positive energy particles are the source. It's called Hawking radiation. The revelation that something can escape the grip of a black hole shocks the world.
When I first announced the results of my calculations, I was greeted with incredulity. By their definition, black holes are not supposed to emit anything.
Hawking proves that while gravity sucks in the negative particle, quantum mechanics allows the positive particle to escape. The two theories can work together. It's the closest anyone's ever come to a theory of everything. But this is all theoretical. No one has ever seen evidence of a black hole. Then in 1971, a scientist in Canada observed something in space that emits powerful X-ray signals. It looks like the core of a collapsed star. Cosmologists around the world wonder if it could be a black hole. It's known as Cygnus X1. Stephen Hawking, in particular, is gripped. He makes an unusual wager with fellow physicist Kip Thorne.
This is my bet with Stephen. Whereas Stephen Hawking has such a large investment in black holes and desires an insurance policy, and whereas Kip Thorne likes to live dangerously, Stephen Hawking bets 1 year's subscription to Penthouse that Cygnus X1 does not contain a black hole. This is signed in 1974.
I had done a lot of work on black holes, and it would have been wasted if it had turned out they didn't exist. But at least, I would have the consolation of winning my bet.
Scientists believe Cygnus X1 was once about 40 times the mass of our Sun. The data shows it has now shrunk to just 5 times the mass. But its gravitational pull is enormous. It can only be a black hole.
It was this euphoria that these things we're studying, they're really out there.
And Kip Thorne wins his bet.
I won a subscription, a 1-year subscription to Penthouse magazine. You have to remember, this is the 1970s. That might not be politically correct today.
Stephen Hawking's theories rely upon the existence of black holes. Cygnus X1 finally proves they do exist. Stephen Hawking is on a quest to unite the two opposing sides of modern science: general relativity and quantum mechanics. If he achieves it, he will have a theory of everything. One equation that could reveal the underlying plan of the universe. It might even explain how it exploded into being. To find it, Hawking needs to piece back together an explosion that detonated 14 billion years ago, the Big Bang. But how? His starting point is an astonishing prediction. Black holes explode, and in a way that makes them very similar to the Big Bang. So Hawking's question is, could anything come out of the black hole when it explodes? If it is similar to the Big Bang, will it release a high-energy stew of particles, like in the early universe?
An understanding of how black holes create particles will lead to a similar understanding of how the Big Bang created everything in the universe.
It could be a mini version of the moment of creation. But all of this is theoretical. No one knows if black holes do explode. Now, for the first time, we may actually see this happening. On June 11th, 2008, NASA launches a state-of-the-art telescope called Fermi. The telescope will search the vast expanse of space for the last gasp of a tiny black hole. Steve Ritz is the lead scientist.
What we'd be searching for is a tiny object, a microscopic object, no bigger than an individual proton, the core of a nucleus, and yet it's shining apparently like one of the brightest objects in the whole sky.
But Fermi's search for these black holes isn't easy. There's a flood of gamma rays from exploding stars that could mask an exploding black hole.
So here's what the whole sky would look like if you had gamma ray eyes. We'd hope to see the individual black hole at the very end of its lifetime making an explosion. And that could happen really anywhere on this image. And that's why it's so incredibly interesting, because one of those contributions could be the individual primordial black holes producing their Hawking radiation.
Ritz's team continues to search for a black hole explosion caused by Hawking radiation. These events are rare, but the payoff is huge, so the search continues. While Fermi searches for clues to how the universe kick-started into life, Hawking's uncovered a mystery that could derail his quest for a theory of everything. In the moment after the Big Bang, something strange happens to gravity. For some reason, it suddenly changes gear and gets weaker. And this is crucial to our existence today. Gravity is actually the least understood force in nature. It's much weaker than the other forces. Consider electromagnetism, for instance. Electromagnetism is the force that tears up our skies in violent storms. It also binds atoms together into everything we see around us. At the instant of the Big Bang, scientists think electromagnetism and gravity are the same strength. As the universe expands, gravity dramatically weakens. Sean Carroll is a cosmologist who studies gravity at the moment of the Big Bang.
Gravity is something we notice every day. We drop things. We have to work against it to climb a set of stairs or to move around. It seems to us like a powerful, important force in our lives. So the puzzle is that, in fact, gravity isn't really as strong as we think. I can take something very, very tiny, like a set of keys, and if I drop it, it could smash something far below. Nevertheless, something as small as this magnet can be more powerful than gravity just because the electrical and magnetic forces here are intrinsically more powerful. Just a tiny little magnet is able to overcome the gravitational force exerted by the entire Earth.
Nobody knows why after the Big Bang, gravity changed gear and became weaker. Hawking's theory of everything should reveal the inner workings of the universe, but it can't explain this. Something is wrong with the blueprint. He sets to work trying to puzzle it out. He now has the top minds in the field working with him. But only a few members of this inner circle can understand his speech. He must painstakingly dictate his scientific papers. The process is slow, but he is making progress. His family worry he is pushing himself too hard.
There was always this terrible, terrible fear whenever anything went wrong, or when he started choking or coughing, or he got an infection, that this was it. Because you just never knew what might happen next.
Then in 1985, on a trip to Geneva, Switzerland, tragedy strikes. Aged 44, Hawking collapses with pneumonia. An emergency tracheotomy saves his life, but severs his vocal cords. Unable to communicate, completely cut off from the world, Hawking plunges into his own black hole. 6,000 miles away in Lancaster, California, speech software designer Walt Woltosz gets an urgent call from a friend about a new client.
He mentioned that he was a physics professor at Cambridge. I said, gee, that sounds like Stephen Hawking, you know, and he said, well, I'm not allowed to say. And I said, well, I'll tell you what, if it is, I'll donate whatever he needs.
Hawking is able to make a slight movement with his fingers, so he can use a switch. Waltos designs an ingenious system that helps predict the words Hawking will use.
I choose the letter B, and I'm going to choose the word black here. Now, after I selected the word black, and in Stephen's case, the word black is almost always going to be followed by the word hole. Now, if I want to speak that, I can just choose the speak command here.
Black hole radiation.
Waltos sends the machine to Hawking, and the voice we hear today is born.
I like my present voice, even though it has an American accent.
Hawking returns to Cambridge and click by click presses on with his work. He employs a team of graduate students to help with the computations. He's been given another shot at cracking the theory of everything, and he's more determined than ever. Stephen Hawking has spent 3 decades trying to discover a theory of everything, a powerful set of laws that governs the entire universe, from the tiniest particle to the largest galaxy. It's been the holy grail of theoretical physics for over a century. Hawking painstakingly lays the groundwork for this theory, but he could be beaten to the finish line by a radical new theory, string theory. One of its architects is physicist Michael Green.
It represents such a profound change in our way of thinking of the universe, both in the very small and in the very large, that it should have all sorts of repercussions.
String theory could even be a candidate for the theory of everything. It unifies every single thing in the universe, from atoms to stars, planets to people, because they are all made from one ingredient, strings. Strings are the building blocks of everything we see around us. The entire universe is a gigantic mesh of these vibrating strings.
We're all made of string, and we're moving in a stringy space-time, and everything is stringy.
To correctly describe our universe with string theory requires something incredible. The world we see around us is made up of 3 spatial dimensions: width, height, and length. But Green and his colleagues think that we are actually surrounded by at least 9 dimensions. This may sound like science fiction, but Green suspects these extra dimensions are hidden from our view.
Clearly, since we don't see these extra dimensions in everyday life, they must, in some sense, be very small and not directly observable.
Green collaborated on his theory with Caltech physicist John Schwartz.
We have the perception that we live in this 3-dimensional world, even though it may in fact be more dimensions.
But how can there be dimensions that we haven't noticed?
This is a line, which is a 1-dimensional object. But if we turn it around and look inside, we can see that it's actually a rolled up piece of paper, which is a 3-dimensional world. We can see that there's an inside, and if we put an ant in here, the ant can go around in 3 directions. So the ant sees it as a 3-dimensional world.
The extra dimensions reveal themselves if, like this ant, you're small enough to see them. Schwartz believes these extra dimensions are curled in on themselves, curled up into tiny knots that are so small we can't see them.
But the fact that we don't see them doesn't mean that they don't have a profound effect on the universe we live in.
Schwartz and Green believe these extra dimensions explain why gravity is so weak. They believe at the moment of the Big Bang, gravity is strong, but then the universe expands. Gravity spreads out into the extra dimensions, weakening as it goes. This explanation removes the final stumbling block to the theory of everything.
Let's consider an analogy in which gravity is like music. When I'm close, it's loud, and as I walk away, it gets quieter.
The music disperses in different directions. As it does so, it weakens.
Here, the music is almost inaudible, and that's because it's spread out over space. Now imagine, instead of music, that we're talking about gravity, and imagine that there are extra dimensions in space. Extra dimensions in which the gravity can spread out even more.
More dimensions in space mean more directions to spread across. This in turn makes gravity even weaker. String theory explains how the universe we see today exists. After the Big Bang, as the universe expands, gravity spreads out through these tiny extra dimensions and weakens. Gravity weakening is what stops the universe from collapsing back in on itself. It's the missing piece in Stephen Hawking's quest for the theory of everything. He concedes that Green's string theory is the best contender to explain how the universe came to be.
Stephen Hawking's relation to string theory is very intriguing. I think he's a big admirer, but not necessarily a believer. His ideas have had a profound influence, actually, on many things that have happened in string theory. And with a bit of luck, string theory has had some influence on his ideas as well.
We believe that there is one fundamental theory that describes dimensions that are curled up so small that we don't notice them. Nevertheless, these hidden dimensions affect physical quantities like gravity.
One hitch is that none of this has ever been proved. String theory and the extra dimensions exist only on paper. Like so many of Hawking's own discoveries, there is no proof. But that might be about to change. And the earliest moments of the universe could soon be revealed. This is the CERN laboratory in Geneva, Switzerland, home of the Large Hadron Collider, the biggest experiment ever built. Deep below ground, scientists are attempting to recreate the conditions that existed just after the Big Bang, to reveal how everything around us came into being. Scientists will search for clues to what happens in the high-energy environment, like the one that followed the instant of creation. It's the moment Stephen Hawking has been waiting for. Scientists will fire subatomic particles in opposite directions. The particles will travel for almost 17 miles, accelerating to close to the speed of light. Then they will slam into each other with a force trillions of times more powerful than dynamite. This high-energy collision will produce particles similar to those in the aftermath of the Big Bang. It should reveal the key ingredients of the universe, and possibly the recipe behind them. The Large Hadron Collider will take us as close as humanly possible to the moment of creation. And in an incredible one-two punch, it could prove that both string theory and Stephen Hawking are right. String theory predicts that we are surrounded by tiny extra dimensions. These extra dimensions trap gravity. If this is true, particles colliding in a small region could feel ultra-strong gravity. This could trigger matter to collapse in on itself into a mini black hole, exactly as Hawking predicts. So rather than a Big Bang machine, the collider could become a black hole factory.
The black hole might actually grow because over time, the black hole will pull material into itself. It could grab onto molecules in the atmosphere. So its mass will increase. I have no idea what will really happen in that case, but that means that the experiment does need to be controlled well.
Researchers estimate it's theoretically possible they could create mini black holes at the rate of 1 per second. Some people fear that just one black hole could swallow the Earth. It's a terrifying thought. Scientists at CERN, however, are putting their faith in Stephen Hawking. Hawking predicts that small black holes will evaporate. They should burn up almost instantly, lighting up like a Christmas tree.
They will produce little black holes, which will then radiate and decay and disappear according to what Stephen Hawking predicted many, many years ago. And that would be, of course, truly exciting.
If black holes do appear, it will reveal the secret of why gravity weakens after the Big Bang. Tiny extra dimensions in space.
If they found proof of extra dimensions, I would be completely staggered. It would be extraordinary, because we would have finally found that space had more than 3 dimensions, which is fundamental.
A fault in the complex machinery delays the big startup until spring 2009. Even then, it may take years to comb through the data for proof of extra dimensions and tiny black holes. After searching for a theory of everything for almost half a century, Hawking desperately wants to live to see the culmination of his life's work. So once again, he faces a battle against time.
There are grounds for cautious optimism that we may now be near the end of the search for the ultimate laws of nature, though much more work will be needed.
But Stephen Hawking can't afford to wait for their results. He's forging ahead and working on a refinement to the Big Bang theory itself. If the Big Bang happened once, could it have happened again? And again? And again? If so, could there be other universes beyond our own? Welcome to the multiverse. Hawking has contributed to the work on the subject by Bernard Carr.
I think Stephen will not be satisfied until he understands not just this universe, but any other universe out there.
Hawking believes we must think of our entire universe as being contained inside a bubble. A bubble which is surrounded by other bubbles, each of which holds a whole other universe.
Maybe there is a whole multiverse of bubbles, of which our universe is just one. And we are just one tiny patch of one of those bubbles. Some bubbles are big, some bubbles are small.
Many small bubbles would appear and then disappear again. A few of the little bubbles, however, would grow to a certain size at which they are safe from recollapse.
So we are just one of many bubbles that survived.
But if there are many, many bubbles, however low the probability of life, with millions and millions of bubbles, there's bound to be life and complexity somewhere.
It's an astonishing thought. If we do live in a multiverse that may contain other forms of life, can we ever hope to reach out to our neighbors?
It is very hard to see how one could travel from one universe to another. People have talked about the possibility of time travel or of wormholes that might connect different universes. So it is conceivable that it would be possible, but maybe that's optimistic.
So will we ever know if these other universes exist? And if so, what would they be like?
It may be a long time before we answer those questions. We may never answer all those questions, but it's the quest which is important. And Stephen is one of those people who's leading the quest.
Stephen Hawking is nothing if not a fighter. He has taken on the biggest mysteries in the universe and cracked them. He found the birthplace of the universe. He forced the two opposing sides of modern science together to prove that it is possible to escape a black hole. An achievement he has mirrored in the battle with his disease.
The greatest thing I've learned from my dad is if you fall into a black hole, don't give up. You can get out of it again. And that's so clearly what he's done with his life.
Hawking has outlived his death sentence by over 40 years to become one of the longest surviving sufferers of amyotrophic lateral sclerosis in the world. But questions remain, and a single equation powerful enough to describe all of existence still eludes him.
Stephen's grit, his stubbornness, have contributed to his continuing vigorously ever so much longer than anybody ever expected. And I'm hopeful that he may still be around working on this 20 years from now.
Stephen Hawking is as determined as ever to find a definitive theory of everything for our universe.